Okay, next I want to talk about the electromagnetic spectrum. And electromagnetic energy is energy that's all around us. It's emitted by the sun. It's warms the earth. It's also emitted by the earth back out into space and by just objects in general. And it comes in a different wavelengths, from shorter wavelengths to longer wavelengths. And shorter wavelengths are higher energy objects give off shorter wavelengths like powerful gamma rays or X-rays, all the way down to the longest wavelengths, which are things like Wi-Fi signals or radio signals. And it's hard to really put it into a figure like this because it's such a long spectrum. I'm going to include a video clip that kind of talks a little bit more about the total length of the spectrum of energy. But I will highlight this part here, and we have, this is the visible light. And visible light is a very narrow part of the electromagnetic spectrum, but it's a very important one. And then it goes from the very dark blue or violet at the shortest wavelengths to the red at the longer wavelengths. And when you get past red, stuff that we can't see, we mentioned in the remote sensing section, you get into the infrared. And when you get below the shorter wavelengths in violet, you get into the ultraviolet. And then it keeps going from there. Now, the reason, here's kind of a closer view. When we say wavelengths, energy travels in a wave, and higher, more powerful energy comes in shorter waves. Less powerful energy goes in longer waves. And why are they more powerful? Well, it depends on the temperature of the object that's emitting this energy. So the hotter the object is, the shorter the wavelength it's going to give off. So this is showing temperatures related to wavelength. And probably the most important aspect for us right now is the difference in the wavelengths between the sun and the earth. Which one is hotter? The sun is hotter. And because the sun is hotter than the earth, it gives off a shorter wavelength of energy, including that visible range. Visible light is right in the wheelhouse of the type of wavelengths that the sun is giving off. So here, this is showing visible light, showing the wavelengths of radiation from the sun. And at its peak, it's in that visible light range. On the other hand, the radiation emitted from the earth, as the earth warms and kind of emits energy back out into space, the earth is not as hot as the sun, so it's going to be emitting longer wavelengths, what we call the thermal infrared, kind of heat energy, heat being kind of emitted from the earth. So there's a difference in the wavelengths of energy from the sun and energy from the earth. Sun is shorter wavelength, earth is longer wavelength. So that's the first part of this. All right, so just to recap, this is all part of what we call electromagnetic energy. It comes in a spectrum of wavelengths, and this is the type of energy specifically transmitted from the sun or emitted into space by Earth. And so what I want you to bear in mind, because this will be important, is that the sun is giving off shorter wavelengths because it's hotter, and the Earth is giving off longer wavelengths because it is not as hot. It is a cooler object than the sun is. So the wavelengths of energy are different. And when we're talking about it, that the different wavelengths of energy will approach the Earth. The atmosphere of the Earth does a good job of blocking some of the most dangerous stuff, such as ultraviolet or X-rays. But visible light can pretty easily be transmitted through our atmosphere. And that's one reason we're adapted to see visible light. Visible light is the type that we can see with our eyes, and one reason for it is because that type of light is very abundant on the Earth, because it's heavily transmitted by the sun and can also make it through our atmosphere. So it gets through. Here's another way of looking at it. This is kind of a fancier figure than this one from the book. This is showing the shorter wavelengths of the sun, and some of it is blocked by the atmosphere and the visible part is not. The visible part can make it through our atmosphere pretty easily, then this is the wavelengths of the energy that's emitted by the Earth back out into space. So shorter wavelengths from the sun, including visible light, longer wavelengths, which is essentially heat given off by the Earth. All right, so one thing we want to discuss in terms of those wavelengths is how the different energy interacts with the atmosphere. So this would be a good point to stop and talk about the composition of the atmosphere. So the atmosphere is the gases that surround the Earth. It plays a lot of important roles. It blocks some of that more dangerous energy from the sun. It maintains the constant, maintains the temperature of the Earth. And let's talk about what is in the atmosphere. We can break down the atmosphere into two parts: the permanent gases and the variable gases. And permanent gases are called so because they don't really change in the percentage, they don't really change too much in terms of their percentage. That the number one, most of the atmosphere is made up of nitrogen, 78%. Number two is oxygen, about 21%. And if you add those up, one thing you should notice is that you're already to nearly 99% of the atmosphere just by nitrogen and oxygen alone. There are other permanent gases, but we'll just stick with the top two. Now, much smaller percentages are the variable gases. And I'll go with the top two here again. Water vapor, which can vary from 0 to 4% of the atmosphere on any given time, and carbon dioxide, which varies in how much carbon dioxide is in the atmosphere over time. And that one's going to be important because we're going to come back to that. So these two variable gases, so carbon dioxide, I want to point out, very, very small, like 4/10,000ths of, like 4 parts per 10,000 of our atmosphere, much less than 1% of our atmosphere, but it plays an important role in the warming and maintaining of the temperature of the Earth. Now, water vapor does the same as well, but we're going to pay particular attention to carbon dioxide because water vapor doesn't really change that much over time, but carbon dioxide has for human reasons as well. All right, so just to recap, we have the shortwave radiation from the sun, part of visible light primarily, a little bit of ultraviolet, a little bit of near infrared. Near infrared being just kind of just beyond what we can see with our eyes. And then we have longer wave radiation being emitted out from the Earth. This is what we call thermal infrared. It's well beyond red, but it's kind of like, you ever seen like night vision things? What those are measuring is this type of thermal infrared. Like a night vision scope is measuring the heat that's coming off of objects like people or tanks or cars or whatever. But the Earth as a whole also gives off this type of thermal infrared energy. So what happens is the sun heats it up, and then as the atmosphere heats up, then heat is given off by the atmosphere back out into space. Now, we're going to be talking about those variable gases, and so we have shortwave energy from the sun and long-wave energy from the Earth. And I want to just think about this conceptually. Like, if you have a greenhouse, how does a greenhouse work? If you close all these doors and windows up, how is the temperature going to change in the greenhouse? Maybe a more familiar situation, if you have all your windows rolled up in a parking lot on a hot day, and you don't use a sunshade, your car is going to heat up. And the reason for that is because windows are transparent to visible light because we can see through them. That means that visible light from the sun can travel through these windows and it can warm up the interior of the greenhouse. Likewise, it can warm up the interior of your car. Now, however, inside the greenhouse or inside your car, longer wave thermal infrared heat energy is being built up. Now, while the sun's rays can go through those windows quite easily, the heat from inside cannot travel through them as easily. They tend to insulate the heat inside. That's how a greenhouse works to maintain warmth even in a cold climate. Also, why your car gets so hot in a parking lot on a hot, on a sunny day. And the atmosphere, because of these variable gases, does something similar to the glass in your car or your greenhouse. That the shortwave radiation can penetrate the atmosphere quite easily. That visible light comes right through. However, the variable gases in the atmosphere tend to insulate some of the heat that's leaving the Earth. And this is known as the greenhouse effect. So the greenhouse effect slows the release of this long wave energy, this energy that's the heat being emitted from the Earth. So just to recap, we have shortwave energy coming in from the sun, primarily visible light, that's warming the Earth, and then heat that's escaping back out into space, which is longer wave energy. The greenhouse gases, they slow down that escaping long wave energy. Now there's a number of greenhouse gases, but I'll focus again on the top two, carbon dioxide and water vapor. Also note that those are the top two variable gases. So those are the top two variable gases, and they're the top two greenhouse gases. Now, we're not going to get too far into climate change now. We're going to be covering it later, but this is a key element when we talk about climate change. This is the mechanism which is part of the change of our changing climate. Now, when it comes to climate change, if you think about what do you read more about, or what are people more concerned about, carbon dioxide or water vapor? Turns out mostly it's carbon dioxide. And the reason for that is because humans are changing the amount of carbon dioxide in the atmosphere, where humans are not really modifying the amount of water vapor. The amount of water vapor that is there would have been there. But carbon dioxide is a little different because, well, let's talk about it. For a while, people didn't really understand how much, they didn't really know how much carbon dioxide was in the atmosphere, and they didn't know how that changed over time. So in the late 1950s, a guy named Keeling set up an experiment to actually try to take a good measurement of how much carbon dioxide was in the atmosphere. And so they set up this measurement on top of Mauna Loa. It's a high volcanic mountain in Hawaii. So you might think of Hawaii as being kind of tropical and beachy, but there's a really high volcanic peak. In fact, if you measure it all the way to the seafloor, it's taller than Mount Everest. And so up on top there of that mountain is a really good place to take a clean sample of the atmosphere, because Hawaii is out in the middle of the ocean. There's not as much influence from cities or factories or things nearby. And so at this Mauna Loa Observatory, starting in the late 1950s into the 60s, they started taking good measurements of carbon dioxide in the atmosphere. Now, I'm going to include some clips that kind of talk about this, and you'll see one thing they thought is, well, they thought it might be, experiment might have gone bad because they saw that the amount of carbon dioxide over the course of a year or so was fluctuating up and down. Right? But it turned out there's a reason for that. That has to do with the seasons of the Earth and how much vegetation is growing in the northern hemisphere versus the southern hemisphere. But more alarming was over time that while it goes up and down, there is also this upward trend, right? And that's something that, so for the first time, scientists kind of had an idea of how much carbon dioxide was in the atmosphere, and also how it was changing over time. And this kind of became alarming because it was coming up and not going down. All right, so you should know what this is. This is called the Mauna Loa curve. And the Mauna Loa curve specifically is measuring carbon dioxide in the atmosphere. And I want you to know that. What is being measured on that Mauna Loa curve? Carbon dioxide. A couple notes about it. It is, the most notable thing is its increasing trend. It's going up, it's not coming down. There's also this sort of yearly pattern, and I'll kind of show that in a graphic in a moment. That's due to changes in photosynthesis during the year on Earth. By the way, this is also known as the Keeling curve also. So the Mauna Loa curve, also known as the Keeling curve after the scientist who set up the experiment. Now, these wiggles, the things that go up and down, the reason for that is because there are more forests in the northern hemisphere than in the southern hemisphere. And one thing we've learned is that you have different seasons, opposite seasons in the northern hemisphere than the southern hemisphere. So when all this stuff up here turns green, that is plants growing and sucking up carbon dioxide, so the levels go down. But as they senesce, they go back into wintertime. They're respirating, releasing carbon dioxide, and the levels go back up. So this seasonal pattern is what causes that yearly variation. Now, one thing, and we'll cover this in more depth later, though. They had it from about 1960 on. They see the increasing trend, and one thing we've been able to do since then is gather some data from nature to try to put this in context. So this is that Mauna Loa curve from 1958 on. Then scientists have been able to connect that with information from that they've collected from ice and ice sheets, and been able to measure going backward in the past, which the ice isn't as accurate, but it gives you a way to kind of try to tell a bigger story. So this Mauna Loa curve is part of a bigger story that scientists are figuring out of how carbon dioxide levels have changed on the Earth. Now, specifically, it was pretty level around 1750, and then going into the 1800s is when we start to see the increase. And if you've studied, this coincides with some human history as well, because the increase starts around the time of the Industrial Revolution, which makes sense because people are burning coal and gasoline and other things as an energy source, and that's adding to the amount of carbon dioxide. We'll get into more depth on that. We'll get into more detail on that later when we cover the topic of climate change.